Let's open this box and see what's inside. This box was sent to me from an eBay seller that I had previously purchased something from. They wanted to know if I could open this part up and see what's inside. I'm just as excited as you are, Isaac. Thanks for sending this. Inside this box is the sample and hold circuit board from an old HP measurement device, specifically from the HP 5180A digitizer, also referred to as a waveform recorder. The 5180A, as its name suggests, is able to digitize and store waveforms on its inputs, and it is capable of doing this at a rate of 20 megasamples per second, or one sample every 50 nanoseconds. One of the documents that I found researching the HP 5180A listed the original price of the unit at $32,700. If we assume this price was at the launch of the HP 5180A back in 1983, this would equate to roughly $100,000 in 2023 money, which is actually pretty similar to modern test equipment prices. Now that we've got a good look at this board, let's remove the heatsink and see what's underneath it. The heatsink is held in place with 6 nuts. Overall, the heatsink came off really easily. Attached to the bottom of the heatsink is a ceramic circuit board with a ceramic lid glued on top. This is the main sample and hold circuit, and it's the HP part number 8519-8396. If we take a look at the circuit board, we can see that there's a conductive spring that allows the module to make contact with the PCB. I also noticed at this point that it appears that this 3M adhesive was never actually used. I would have expected this protective layer to have been removed to attach the module securely, but maybe it's left here intentionally. Regardless, this is a pretty simple way to allow the module to be connected to the PCB without soldering it down. We can also see that the back plate has the bolts press fit into it that the nuts were attached to. For the rest of this video, we're going to focus on this piece, the sample and hold hybrid circuit. My goal here is to remove the lid, and I'm going to start by prepping the surface with a razor blade. The idea is to remove everything that could potentially start on fire, since I'm going to be applying a very high heat to this. If I left these labels on, they would burn and no longer be legible. After I've removed all the labels, I'll use some isopropyl alcohol to remove any remaining residue. It's not perfect, but it is definitely better than what it was. Next, I'll mount the device in my vise to hold it as I heat it up. It's bigger than my vise, but luckily I was able to find a place to clamp onto. I'm not exactly sure how this is held on here, but this is not looking promising. I set the hot air temperature to 1000 degrees Fahrenheit, and I started to slowly heat up the entire device. This actually takes a lot of time because the heat frame is efficient at removing the heat. During the process, I'm constantly monitoring the temperature with an infrared heat gun so I don't get it too hot. When the epoxy starts to heat up, it breaks down and can easily be peeled away from the edges with an X-Acto knife. My goal is to remove as much adhesive that's holding the lid on so it's easier to pull off in the next step. Unfortunately, in the next step, the whole device separated from the heatsink, and we can now see that it was simply attached with some thermal paste. My solution to this was to tape down one side with some Kapton tape and heat it back up. I was eventually able to get the X-Acto knife under one of the edges and pry the lid off. I was able to successfully remove the lid without shattering the ceramic circuit board. With the lid removed, we can get a really good look at what's on this circuit board. Right away, we can tell that it has a lot of individual integrated circuits. I was also immediately drawn to the large inductor. There's also a bunch of different ceramic capacitors and some very thick bonds connecting different parts of the circuit board together. After removing the heatsink, we can get a look at the back again, which is completely plated in gold. It looks like they only placed heatsink compound on the backside of where the integrated circuits are. After removing all heatsink compound, we can get a look at this under the microscope. I'll start by looking at some stuff printed directly on the ceramic. For example, here's the HP logo, and the text, sample and hold, to let us know what this is. The part number for this circuit board is 5088-2, and it looks like it's revision D. Next, I'll focus on this grouping of circuits. There's actually a similar grouping of circuits below this. Let's zoom in to get a closer look. This first silicon chip is actually a set of laser-trimmed resistors. Trimming the resistors with lasers allows them to be incredibly precise. There's lots of other versions of these resistors that we'll see on here, but for now, I'll focus on this integrated circuit. According to this document that I found, this is one of 3 high-speed operational amplifiers that were designed for this system. I'm sure if I took the time, I could trace out this entire circuit and confirm it. In this video though, we're just going to look at it. If we zoom in further, we can start to make out the different transistors that were used in this design. I'm not 100% sure, but the top metal on this chip looks like it might be gold or at least gold plated. This chip also has a hidden secret that you may have already noticed. Nestled over in this corner is a silicon doodle of a cat, a mouse. I don't know what this is. What do you think? By the way, the document I mentioned earlier was the November 1982 edition of the Hewlett Packard Journal. There's a lot of great information in this document. Nearby this chip is a set of 3 identical transistors. We can see how they're connected together with the various bond wires. Zooming in closer, we can get a really clear view of what this transistor looks like. If I had to guess, this is the base, this is the emitter, and the collector is on the bottom. Nearby is another laser trim resistor similar to the first one. The shapes and features are all the same, but they're different colors. Not surprisingly, it's also trimmed completely differently than the first one. Nearby this chip is something that I'm not 100% sure what it is. It only has 1 bond wire going to it, so it may be a diode? Once again, let me know what your thoughts are in the comments down below. Moving over to the other side of this group of chips is another laser trimmed resistor. This laser trim resistor also appears to have gold or gold plating on its top metal layer. It certainly is a very interesting looking resistor. Nearby is yet another laser-trimmed precision resistor. This one is different from the other ones, and it even has a very interesting logo, which is of course the upside-down California Micro Devices logo. What's nearby this chip, you might ask? Well, of course, it's another precision laser-trimmed resistor. Wait, this is a resistor, but it's not laser-trimmed. Nearby, however, is the absolute unit of a laser trim resistor. I mean, just look at how many different traces there are. I'd love to see the laser trimming process in action, both from the chip's point of view as the laser ablates the poly layer and the resistance as it goes down. I think it'd be really cool. With that, we can move on to the center section of circuits. Over here, there's only 1 chip to focus on. According to that document, this is a sample gate IC containing a monolithic Schottky diode bridge sampling switch. It's also only 1.3 by 1.3 millimeters in size. Zooming in further, we see similar circuit components compared to the operational amplifier from before. Going by this diagram, I believe that the squares are all the diodes that form this diode bridge. In addition to these diodes, there's lots of other stuff to look at, like these transistors, or these test components. Of course, what integrated circuit would be complete without all of the different layer markings? Below this chip is a set of circuits that are identical to the group that we first looked at above. Moving to the right of this chip, there's a large transformer with multiple coils. This trifler wound transformer has a 2-to-1 ratio and connects the sample gate IC that we just looked at to the gate driver IC that we're going to look at next. The center tap of the transformer is connected here to the V+ voltage. This finally brings us to the last integrated circuit, the gate driver IC. According to that document, this chip generates a high current pulse that has sub-nanosecond transition times. This chip measures 1.28 by 1.28 millimeters. One thing that this chip has that the other ones don't is every pin is marked with what it does. This would make tracing out this circuit a much easier task. Just like the previous chip, this one includes test circuits and all of the layer marking. Zooming into this chip, we can see that it uses the same type of transistors that the previous two ICs have used. Zooming out, we can look at the last laser trimmed resistor. It's actually trimmed very similarly to one from earlier in the video. Moving further to the right, there are more symbols and text to look at. For example, there's samp and not samp, the differential sample input. There's also D next to a ground symbol, which I would assume means digital ground. Around the circuit board are also very thick pieces of metal that have been bonded instead of wire bonds. My guess is that these would be for larger current carrying capacity. You can also see all the places where I scratched the gold and the places where the conductive spring made contact with the pads. There's a lot of other symbols and markings on here that I'm sure would make more sense if I read more about this in the document. With that being said, that's going to do it for this video. If you enjoyed this video and haven't already, you should consider subscribing. That way you won't miss when new videos are posted. In the meantime though, if you haven't gotten your fill of integrated circuits, I have plenty of other videos for you to go and check out. And if you want to see what I'm working on in between videos, you should consider joining the Discord server. As always, thanks for watching, and I'll see you in the next chip.